Hi, I'm Dr. Sook-Lei Liew, and I'm excited to talk to you today about REINVENT, a VR brain-computer interface for stroke rehabilitation that we've created. As many of you may know, stroke is a leading cause of adult long-term disability worldwide. And for people who have really severe motor impairments after stroke or can't move their arm after at all, rehabilitation treatments are really limited. So one promising avenue for therapy is to use brain-computer interfaces, or BCIs, which teach people to directly control their own brain and muscle activity. And this is kind of a backdoor way to improving, ultimately, control of the affected arm. My first and earlier exposure to BCIs was when I was working at the NIH, and here we gave what's called real-time fMRI neurofeedback. So I put people in a big MRI scanner in which it was non-invasively able to read out their brain signals, and they're able to see this screen that I'm showing here. And what we told them is when you see the circle turn into a red triangle, we want you to actually try to control brain activity in motor regions of your brain. And you can do this without moving and simply by thinking. Most commonly, people are able to control these brain regions by thinking about movement, though. So trying to imagine movements that you've done before. And what this looks like is when the triangle turns red, this fluctuating bar is indicating brain activity in their sensory motor regions. And over the course of a few seconds, they are able to increase that brain activity using only their thoughts. And so that you can see they're not moving. And outside, we can see the brain regions that we're recording from and the signals going up and down in accordance with our stimulus. So we actually did this with people who are both healthy and people who have had a stroke, and showed that both populations are able to learn to control their own brain activity using this type of BCI. However, there were some critical limitations to making this clinically relevant. First of all, the expensive, such as an MRI scanner, is expensive and not widely available to everyone. Secondly, the feedback, as you see from the thermometer, is relatively boring, so it just goes up or down based on their brain activity. But the third thing, and the most important, is that the way that we were presenting feedback and the way that feedback in BCIs is often presented is almost like a dual task paradigm. And what I mean by that is that to control motor regions in their brain, people usually have to close their eyes to imagine in detail some sort of movement that they're familiar with. And then they open them every so often to see if the feedback actually moved, to see if they did the task correctly. So moving forward, we wanted to create something that was portable and accessible to more people, that was engaging in terms of the feedback, and that provided a type of feedback that could naturally activate sensory motor regions in the brain by itself. So as opposed to a thermometer, which is something very difficult, we wanted to provide more naturalistic feedback. So to do this, we replaced the MRI with EEG, and what's shown here. This is a more portable version and a way to read out brain activity using non-invasive electrodes placed on the scalp. And we, of course, provided the feedback in virtual reality. As you know, there's a lot of reasons to use virtual reality in rehabilitation, but the key one for us and for this project was the fact that when you're in VR, you feel really immersed in the environment and you can embody whatever avatar you're given. So if your avatar is, for instance, standing at the edge of a skyscraper, you might actually start to show physiological signs that make you feel like you too are standing at the edge of a skyscraper, even though you know you're just sitting at home. So your palms might get sweaty, your stomach might have butterflies, and your heart rate might increase. Similarly, people have shown that we can embody any type of avatar that we're given in VR. So if you're shown a child's body in VR, you're likely to show more childlike behaviors. If you're given the body of a more attractive avatar in VR, you start to behave more like a person who believes themselves to be very attractive. So what we wanted to know is, can we give somebody who has motor impairments after stroke and who can't move the ability to control a healthy avatar in VR that can move? And will this induce neuroplasticity that leads to motor recovery? To do this, we created a system called REINVENT, and it takes brain and muscle signals that indicate somebody's trying to move and gives them feedback of their own arm moving in virtual reality, even though their real arm doesn't move. What this looks like in practice is something like this. So this is one of our participants who's had a stroke, and he's wearing an EEG cap. So we're reading out brain signals, especially from both sides of the brain, but we're using the signals on the side that was damaged after stroke. He also has a VR headset, and what he sees in here you can see on the screen. And we're also recording muscle signals from him to see if that in the future could also be a viable option. So what happens in this paradigm is that you'll see a ball come up to the table, and the goal is for him to move his virtual hand towards the ball so that it pushes the ball off the table again. As you can see, he has very limited actual arm movement, but the movement that he sees of the virtual arm is driven by his brain. So this is one way, for instance, to reinforce those good brain signals that would ultimately be able to control his virtual or his real arm. We can also do this without using the EEG headset. So for some people who have more muscle activity, even if it's not enough muscle activity to see an entire movement like a wrist extension, if they have some muscle activity, we can try to train that. And so what you see in this video is just using the muscle activity, which you see signals here, and it's going to drive the movement of the virtual arms. Let me go back here. So the virtual arm movement is based on the muscle activity that we see coming from this participant. So these are two different ways to provide feedback. We've been using reInvent and doing a lot of tests to look at the effects on brain and brain to muscle connectivity over time. And so far, our preliminary studies indicate that most people are able to learn to control their own brain activity or muscle activity when training with reInvent. And after repeated sessions of reInvent, so anywhere from 6 to 10 to 20 sessions, we do see that brain activity in sensory motor regions on the lesioned hemisphere improves, and we see greater connectivity from the brain to the muscles of the affected hand, which ultimately that's the pathway that will improve actual motor function. Our latest step is to create what we call tele-reinvent, which is a home-based system, which I'm sure everyone can understand given the current pandemic situation. We need more options to make this more accessible so that participants don't have to come into our lab to do the experiment. So we've created a system that's just a laptop. We Zoom with the participant and they show us the video of how they've placed the electrodes. In this case, we just are using the EMG or muscle electrodes. And then we provide clinician guidance and we can see their signals in real time. And perhaps most importantly, we've tried to make the games a lot more immersive and fun. So we have a whole arcade and we're building out a suite of arcade games for them to play. And again, all of these games are controlled using their muscle activity. So for instance, there's skee ball and you can hit the skee ball towards the targets based on your muscle activity. There's also a game called Blinko, which is kind of like Blinko maybe. And the movement and placement of the puck is driven by also the muscle activity. And we are now working on integrating VR into this. So all the games are already in 2D and 360, which you can view on our 360 playlist. But the VR part, it does have some considerations because of safety and things like that. So that's the next part that we're working to integrate so that people can ultimately do this type of VR-based BCI training at home. All right, with that, I would give a huge thanks to the team that's worked over this over the years. On the top are the current team members, and on the bottom are people who have worked over it all over the years. Huge thanks to our participants, and thank you all for listening. Fight on.